Now let's begin 11.4 comparison tests. And in this section, we deal with two types of testing. One is comparison test, which is summarized in the first box. And then the second is the limit comparison test, which is a little bit more useful in the second box. The strong limit comparison test, that's not as important, and I'll talk about it probably in the next video when we do all those proofs here. Now I'm not going to prove this comparison test in this video. In the next one I will, but let's use intuitive understanding to get through with this comparison test. We have this two positive term series where Bn is greater than or equal to An, and first comparison test says even the bigger series is bounded, then smaller series is also bounded. And we are talking about positive term series, so bounded positive series always converges because the sequence of partial sums is bounded and increasing. How about the next one? Well, this time even the smaller series is unbounded, so bigger series is also unbounded, and that's really dull. And as you have seen here, the proof of comparison test is actually a little bit tricky, but intuitively it's easier to understand. Even bigger series is bounded, then small series is also bounded. Great. And even smaller series is unbounded, then bigger series is certainly unbounded. That's basically it. Now limit comparison test is a little bit trickier, but it'll turn out to be a little bit more useful. Why is it more useful? It'll turn out that dealing with inequalities can be tough, possible but tough. But this time you're dealing with equality, so that's a bit easier. If the limit of the ratio is L, which is neither 0 nor infinity, then both series converge or diverge at the same time. So that's a limit comparison test. So An is given. It is a matter of getting appropriate Bn so that the limit of the ratio is neither 0 nor infinity. Typically you'll be able to find that Bn where this L value is 1. In that case, we say two series are asymptotically equivalent. And the reason we call it asymptotic equivalence is because if you actually graph them, then we have really asymptotic behavior. Those two graphs asymptotically, they closer and closer as you move to the right hand side of the left hand side, typically right hand side in this case. Do we have some picture? Oh yes, good. We have a couple of series here, but expressed as functions, and as you can see, blue and red function are getting closer and closer and closer as we move to the right. We have asymptotic behavior, and that's why this kind of thing is called asymptotic equivalence, and that'll turn out to be pretty useful. And let's move on to example 4.5. As a matter of fact, even this very first example is hard. Let's make this problem a little bit easier. And let's do this. Okay. Instead of starting from 0 or 1, I'm starting from 2 so that the denominator never becomes 0. If you have something like this, then it's relatively easy to use the comparison test. And this one is greater than or equal to 1 over square root of n. Why? Because square root of n minus 1 is smaller than square root of n. If you reduce the denominator, then you are increasing the fraction, isn't it? Or you can actually test those by plugging in some value. Plug in n equals 2, then you have 1 over square root of 2. Plug in n equals to 2, then you have n over square root of 2 minus 1. Well, certainly bigger. Anyway, we have something like that. And then what do we have? The series for 1 over square root of n is infinity because this is a p-series. So the original series, which is actually bigger series, must be unbounded as well. So you can conclude kind of like this using the comparison test here. The key observation was this one. Compare that with smaller series, but even the smaller series is unbounded. Consequently, the original series is also unbounded. Now let's try to do the same thing with, well, this problem A. Let's try to do that, then very soon we are going to come up in, very quickly we are going to come up with a trouble. And then if I compare that with 1 over square root of n, this is what I'm going to get, because if I increase the denominator, then we're going to decrease the fractions. So this right hand side is bigger. And then this sequence, this series, excuse me, the right hand side series is unbounded. So what conclusion can I get from here? The original series, which is smaller series, it's less than or equal to infinity, and this doesn't really tell you anything because this is smaller series. It is less than or equal to whatever you get from the larger series, and everything is less than or equal to infinity here. If it is strictly less than infinity, good, we have convergence. But equal to infinity or less than or equal to, I just get nothing out of it. So comparison test is not working very well in this case. There's a way to make it work, to tell the truth, and it's a bit tricky, but you can do something like that. You can reduce this one even further by doing something like that. In that case, it'll work out. You see, if I multiply by 2 and then make this right hand side, this fraction even smaller, and then this one diverges, then comparison test will work okay. But come on, working out this inequality is not an easy thing. I can do it because I'm a teacher. I've been doing this for a long time. For students, this is not easy at all. Typical thing a student wants to do is to throw away this one, as we have done before, and then get a p-series. But that doesn't work here. So how do we make it work? Instead of using the comparison test, work out with the limit comparison test. So let's throw away this and that, and then throw away this one, and asymptotically this given series and 1 over square root of n are equivalent asymptotically, and the right hand side is unbounded. And of course, if you have something like this asymptotic equivalence, you have to justify it through the limit comparison test, and here it is. It's not difficult computation. The original series and then the p-series, and then do the computation, and then we end up with limit is equal to 1, neither 0 nor infinity. And we know the behavior of the p-series. We already wrote it like that. So we have a divergence here. It's that simple. Asymptotic equivalence by throwing away unimportant terms, and then justify that. Let's do it once again. This time, how do I get a series that is asymptotically equivalent to the original series? Throw away this plus 5, throw away all these unimportant terms, and you're going to get n over n cubed. Well, here, n over n cubed, so we have 1 over n squared, and that one is finite. so we have to have a convergence. And justification, well, the original series over 1 over n squared, and then some algebraic manipulation, and we're going to take the limit that will turn out to be a certain L value, which is neither 0 nor infinity. How about this problem here? 5 to the nth power plus 9 to the nth power. This time, what's the most important term, leading term for numerator? 9 to the nth power is dominating. Denominator, 10 to the nth power is dominating. The others are unimportant because they are much smaller. So we have this kind of computation. Asymptotically, this thing is equivalent to 9 to the nth power over 10 to the nth power. And as a matter of fact, this one is a geometric series. Oops. And 9/10 is less than 1 in absolute value, so this geometric series converges. And of course, here is a justification using the limit comparison test. Let me increase the font here. Oh, too much. I hope this is still visible. And then the original series over the comparing series, and then do those limit computation, some algebraic manipulation. This will go to 0, that will go to 0, and we have limit value equal to 1. Neither 0 nor infinity, so two series behave the same way, and the other series is a geometric series that converges. This one, well, almost equally as easy. This is nothing but an algebraic series, so we can easily find out the growth order of the numerator. This one is not important, square root of n squared, so just growth order is 1. Oh, by the way, that's not important either. And then how about this one? This one is growth order 1, and this one n to the third power to the 1/3 power, so growth order 1. And this one n to the fourth power to the 1/3 power, so we have 4/3 power. That's going to be the growth order of the denominator. And after simplification, we have 1 over n to the 1/3 power. P-value is 1/3, so we have to have unbounded series. And this time, I didn't bother justifying it with the limit computation, but you can insert it. The final example, n factorial over n to the nth power. This one is different. I don't think you can do this with the limit comparison test. Can you? Will that work? No, I do not think it will work. But comparison test will work. The numerator is big, n to the n factorial, so it's n times n minus 1 times n minus 2 times all the way up to 1. But denominator is even bigger. It's n times n times n times n times and so on. So if you stay the head part, the starting part of the factorial, n, n minus 1, n minus 2, they're not too different from n. But if you go to the tail part of the factorial, we are talking about 1 times 2 times 3, and the denominator is n times n times n, so denominator is going to be much bigger. But in order to write it in a little bit more precise form, logically a little bit more precise form, well, we have something like this. Let's increase the font a little bit so that you can see this thing better. Well, you have n factorial in numerator, and n times n times n times that kind of thing in denominator, and decompose everything. We have n over n times n minus 1 over n minus 2 over n, and so on. And what we do, we simply leave the last two and then overestimate everything by 1 because denominator is bigger. So what do we have? This thing is less than 2 over n squared. And what's that? N squared? That's a p-series. P-value is equal to 2. So we have to have a convergence. So the original series converges as well. That was a bit ingenious. So I regard this one a little bit tougher problem. Well, whenever factorial shows up, be careful. It can be rather complicated. But there we go. There goes an example of a comparison test. Otherwise, limit comparison test was more effective.